Reevaluating double star STF-619. When we began our research, the European Space Agency had less than a year ago released unprecedentedly accurate proper motion and parallax data that came from their Gaia satellite. So our goal was to analyze the double star system that was classified as a physical, gravitationally bound system, and use this new data to reevaluate that classification and perhaps show that these supposedly gravitationally bound stars are actually gravitationally independent, or optical double stars. This research is important, as studying double stars helps establish the relationship between temperature, radius, and mass, to therefore more precisely classify non-binaries based on their mass-luminosity relationship. The slide shows the mass-luminosity relationship, which we can study largely because of the double star research. We searched the Washington double star catalog using stellaroscopy, and we ended up choosing to study STF-619. We selected this system because we wanted to make our own observations, and that required the system to be visible during the time of our research. Photographing and resolving the system also meant that the primary and secondary stars needed a separation of at least 4 arcseconds and a sufficiently small delta magnitude, which in this case meant nearly 0. STF-619 not only satisfied these constraints, but its proposed orbital solution required the secondary star to have a period of 490 centuries. The slide shows its orbital solution, plotted in black with the evidence represented by green, blue, and pink points. It seemed unlikely that there was sufficient data to support the solution because the system had only been observed for 2 centuries. As you can see from the slide, there is only evidence for a very small portion of the period of the orbit. This suggests that the existing orbital solution may not be accurate.
Yes, okay. We contributed to the historical observations of STF-619 by making our own measurements. The slide shows the telescope used and one of our images. Because we operated the telescope as opposed to a robot, we were able to ensure in real time that our images were properly focused and unsaturated. In order to find the position, angle, and separation of STF-619, we analyzed 6 of our sharpest images in AstroImage J, a screenshot of which is shown here.
While researching STF-619, we also came across a rectilinear solution published by Scardia et al. In 2017 that included 5 parameters for each star. Scardia's prediction for the time when our measurement was taken is plotted on the graph in orange. The historical data is shown in black. The purple dot shows a prediction based on our XL trend line of the data. The primary star is at the origin. The dots show the position of the secondary star. The ephemerides, predictions of the double star's prediction based on an orbital solution, based on Kiselev's orbital solution from 2009, is plotted on the graph in blue. This prediction is quite different from the point predicted by Scardia's linear solution. The green point is our measurement, which is calculated to be 0.26 arcseconds away from Scardia's linear solution and only 0.19 seconds away from the ephemerides. However, Scardia's prediction is significantly closer to the linear trend line we found with the data using Microsoft Excel.
We also analyzed the proper motions, or PMs, of the stars in STF-619. Proper motion is the movement of a star across the night sky over the course of a year. A way of quantifying the difference in 2 stars' PMs is through calculating the PM ratio. If the 2 stars are close to each other in the sky, and the PM ratio is less than 0.2, they're likely gravitationally bound. But if the PM ratio is greater than 0.6, they're probably gravitationally independent. Based on data from the Gaia de Larice 2, we found the PM ratio to be 0.59. Thus, the stars are likely gravitationally independent. However, we need more evidence to confirm this. The graph on the right shows the PMs we obtained from Gaia. We also analyzed the parallaxes of the primary and secondary stars. By substituting the data provided by Gaia into the parallax equation, which is shown, we were able to find the range of possible distances between Earth and each star. As this table shows, the minimum distance between the 2 stars is 35.4 light years, which strongly suggests that they are gravitationally independent.
Ultimately, we concluded that STF-619 is probably an optical double that is composed of gravitationally independent stars. However, there is still a lot of uncertainty. Although our measurement fits the ephemerides more closely than the rectilinear solution, the linear prediction better fits a trend line of the historical observations. Meanwhile, the proper motion data is ambiguous, although it does tend toward confirming our conclusion. The parallax data likewise suggests that STF 619 is an optical double. If this star system continues to be observed over the coming century, it should become clear with a high degree of certainty whether these stars are gravitationally bound.